Okay, so now it's time to use what we know about partitioning a region under a graph and start to really look more explicitly at calculating upper and lower sums or estimating the area between a curve and a graph. So we have find the upper and lower sums of a region bounded by the graph of f of x equals x cubed and the x-axis between 0 and 2. So what we're really looking at is, well, we know that the function x cubed looks like this. So this is y equals x cubed. And what we want to do is find the area between 0 and 2. Well, we know the value or the elevation at this point. 2 cubed is 8. So we're looking at 2, 8 for a point here. But that doesn't really give us an idea. We could choose one partition and say, well, given the shape of the cubic function, I bet it's half of the rectangle. But we want to get closer and closer to more exact values to describe the area. So let's use what we know and calculate the upper and the lower sum and see where. So the first thing we want to do is decide on some intervals or some widths for my partition. So I could choose, as I said just a moment ago, to make my partition width 2, and then my upper sum and my lower sum would approximate the area, but not very close. If I were to divide this into 2 equal portions, meaning I have 2 partitions, then that would work better. I would get closer, but I think maybe 4, at least for the purposes of this demonstration, would be a not very unwieldy partition value to work with, or number of partitions to work with. So we have a formula when we're calculating the partition, and we have a designation for a value. We call the width of each partition delta x, and this is when our partitions are all the same width. The delta x, or the change in x from one partition to the next partition to the next partition. And a simple formula that's totally logical is b minus a, meaning the greater value minus the lesser value, divided into however many. So the whole length divided into n partitions. So in this case, I'm looking at 2 minus 0, and I want 4 partitions, so n equals 4. So 2 minus 0 divided by 4 is 2 divided by 4, which is 1/2. So clearly that's true. If I were to divide the distance from 1 to 2 into 4 equal pieces, then delta x, each jump from one partition to the next, the base or the width of the first partition is 1/2 unit, and then to the next partition is another 1/2 unit, then a 1/2 unit, then a 1/2 unit. I could choose this to be 1/8. I could choose n equals 8, and then I would have 1/4, or I could choose n equals 5,000, and then I would have almost exactly the area, but I would have a difficult time calculating 1,000 partitions. So we're just going to stick with n equals 4 to play with the tools we have for doing this. So let's start with the lower sum, and it has a symbolic designation, S of n, and notice this is a lowercase s, meaning lower sum. As you might have guessed, the upper sum would have a capital S. So this is the lower sum, and it's the result of taking the sum of the partition areas over the interval that we're evaluating. So the first partition all the way to the nth partition, in this case that would be 4. And then we want to find the function of mi, and I'll tell you what that is in just a second, times delta x. So you can see delta x we've already talked about is the width of our partition. And so mi, since each partition represents an area, if delta x is the width of our partition, then somehow f of mi has to be the height. Well, it is. We're going to take the lowest height on that interval because we're taking our lower sum, and in this case I'm actually looking at no elevation because the lowest point on that interval is 0, 0. The highest point is 1/2 cubed, or 1/8. So for the lower sum, we want to start by taking the area of the lower, the part of the partition that's completely enclosed within that interval. And so our first element is just going to be 0, but that is certainly less than whatever the area is, and that's what we're looking for, is the sum that is strictly less than. the area we're looking for, which is base times the lower height every step of the way. So now we just have to calculate what those are. M sub I means the lowest height on that interval, on each interval. So for interval 1, delta x is already established to be 1/2, but the height is going to be governed by whichever side gives me the lowest height. And so in this case, the lowest height for the first partition is 0. For the second partition, the lowest height is at the 1/2 mark, which is at the 1/8 mark. In the third, I equals, where n equals 3, not n, but in between n, at the third partition, we're looking for the lowest height, and that lowest height for the third partition is going to be at 1/2 cubed, which is 1/8. Hey, I made a mistake here. This is 1/4 cubed, which is 1. Okay, I clearly need a better picture, so let me sketch out a bigger picture I can work with. So we know we don't care about the second, third, and fourth quadrant, and we know the cubic function looks kind of like that. If we're looking at it at 2, then this is at the point 2. The elevation is 8. Our partitions are equally 4 partitions. So we're looking at 1/2, 1, 3/2, and 2. Done. All right, so as I said before, the lower height on the first partition is just 0. The lower height on the second partition is 1/2 cubed, which is 1/8. So I was correct before. The lower partition, the lowest height on the third partition is 1 cubed, which is just 1. And the lowest partition on the lowest height on the fourth partition is 3/2 cubed, so that's 9/8. No, it's not. It's 27/8. But since we're looking for the lower sum and our function is continuously increasing, we can say that the lower height is always on the left-hand side. So for our first partition, it's on the left-hand side. For our second partition, it's on the left-hand side, all the way through. So our lower values are 0, 1/2, or excuse me, our height values for the lower side of the partition start at 0, then 1/2, then 1, then 3/2. And these are the input values for our lower height. So our lowest side length happen at 0, 1/2, 1, and 3/2 for each partition in turn. The highest value, we haven't started that sum yet because we're looking for the upper and the lower. We're looking for the lower right now. But the upper sum values happen at the right-hand side, which means they always, the height, the highest part of the first partition happens at x equals 1/2. The highest part of the second partition happens at x equals 1. The highest for the third partition is at x equals 3/2. And the highest of the fourth partition is at x equals 2. So the input values for the lower and upper partitions shift from one side to the other of the partition in this case. So the height at this stage of the game that we're talking about is really the function of the lower or the left-hand side or the left-hand input. This is very sloppy notation just to make the point, but we're looking for the function at that point. So we can sort of put this together now as a sum. We could say that since we're dealing with 4 partitions, we're looking for I equals the first partition to the fourth partition of f of, I'm going to keep this lower m1 or mi notation for now, times delta x. So how would I find mi? Well, I'm going to do this. I know the intervals I'm talking about are 0 to 1/2, and then 1/2 to 1, and then 1 to 3/2, and then 3/2 to 2. So these are the intervals for each of the partitions. And because it's the right-hand side, I'm going to take the right-hand value in each case and put together my sum. So this would be the sum as I equals 1. Well, I don't have to write that part out again. Sorry about that. I'm just going to put it together. So when I equals 1, meaning my first partition, I'm looking at the f of 0 times delta x, which is 1/2, plus next the f of 1/2 times delta x, which is 1/2. Next, the f of 1 times delta x, which is 1/2, plus the f of 3/2 times delta x, which is 1/2. So the rest of the calculation is just algebra. All four terms have a 1/2, so I'm going to factor that out. And then I'm going to multiply by, well, f of 0 is 0, right? 0 cubed is 0, plus f of 1/2 I've already calculated is 1/8, plus f of 1/2, f of 1 I've already calculated is 1, plus the f of 3/2 is 27/8. Little arithmetic here. See, if I find a common denominator, I've got 1/2 times 8 in the denominator. 27 plus 9 is 36. And so I have 36 divided by 2 is 18 divided by 8, which is 9/4. So I'm looking at 9/4 as the lower sum of the partitions, meaning that 9/4 is less than the actual area under this curve. Okay, so now we can do uppercase S, N, and all that is exactly the same thing. I equals 1 to N times the function of capital M sub I, just meaning the right-hand heights, right, the right-hand values, times delta x. So when I set this up, I don't have to do as much work as I did the last time. I already know, well, let's write this as lowercase n, the lower sum. And so the upper sum is I equals 1 to 4 of f of capital Mi times delta x, just so it matches. Now, I know I'm going to factor out my delta x, but delta x is exactly the same thing in both cases, so I'm going to pull out my 1/2, and now I just want to sum the right-hand heights. So the highest, I'm actually looking at this partition now, where I'm using the right-hand side to get the height of the partition, the right-hand side to get the height of the partition, and I just on and on doing the right-hand side every time. So let's find those values. They're already calculated. So the right-hand side for the first partition is 1/8. Right-hand side for the second partition is 1. The right-hand side for the third partition is 3/2. And the right-hand side for the third partition, oh, it's not 3/2. I'm sorry, I just copied it down. The right-hand side for the third partition is 27/8. And the right-hand side for the fourth partition we already know is 8. So again, a little arithmetic, 1/2 times common denominator, 1 plus 8 plus 27. 8 times 8 is 64, all over 8. So 64, 65, and 15 is 80, and 20 is 100. So 100 divided by 2 times 8. I'm going to keep it factored because it's easier. 50 divided by 8, 25 divided by 4. That tells us that the actual area under this curve is less than or equal to, could be, obviously from the picture it's not, but it could be, we don't know, 25/4, which is 6.25, and greater than 9/4, which is 2.25. So the actual area under this curve is somewhere between these two values. I happen to know, because I've already calculated it, that the actual area equals 4. And 4 is definitely between 2.25 and 6.25. Not very close. We did a whole bunch of logic and a whole bunch of visualization and a fair amount of not too difficult arithmetic to get us to a place where we still don't know the area under that curve. The good news is, tomorrow in our next lesson, we will look at a method that uses this exact same way or these exact same techniques, but we will calculate the exact area under the curve. And I'm going to give you a hint. We're going to bring back our old friend, the limit. And we're going to look as our partition values, n, so the number of partitions we choose, as n approaches infinity. So that means our partitions, instead of having 4 partitions or dividing it in 2 and having 8 partitions, we're going to actually calculate where there are infinitely many partitions. That's pretty cool that we can get away with that. And in fact, this is the same formula we're going to use. So that's the sum. So the limit as n approaches infinity of the sum, I equals 1 to n, so this value is approaching infinity, and a little bit change in notation, f of c sub 1 rather than m1, because we don't need a lower sum and an upper sum. We're just going to find an actual sum times delta x. And you should spend a minute thinking about what happens to delta x, the width of the interval, as n, as the number of partitions approach infinity. Just a little food for thought. Till next time.